Hello and welcome to another video. In this video we're going to be working on string compression 2, and this is the first hard problem of the month, so interesting one. And in the problem it says a run length encoding is a string compression method that works by replacing consecutive identical characters with the concatenation of the character and the number, making the count of characters the length of the run. For example, to compress AABCCC, we replace AA with A2 and CCC with C3, thus the compressed string is less characters. And we're not adding one after single characters, so if it's a single character with no number, it will be assumed 1, and everything else will have a number. Given a string S and an integer k, you need to delete at most k characters from S, such that the run length encoded version of S has minimal length. Find the minimal length of the run encoded version of S after deleting these characters. So in this first example, the optimal scenario is to delete the B and the D, and then you will get A3 C2, which is length 4, because if you delete an A or a C, you'll go from like A3 to A2, which doesn't give you anything, and then C3, you'll go to C2, which doesn't give you anything either. In the second example, a little obvious as well, you want to get rid of the B's, because then you will just have A4. And that's optimal. Because if you delete like A's or 1B or something, you're not going to get enough. Like let's say you delete one of each, you will get A3B, which is 3 characters. If you delete only A's, you'll get A2B2, which is also not optimal. And the last one, if A is this, then return 0. So this problem is pretty tough because they give you like a length, which is kind of small. And so ideally, the thing you want to look for this problem, like right away, is probably kind of two things, right? Is there like a greedy solution, and is there a DP solution, right? Because you're making deletions from all over the place. So typically, when you're making deletions all over the place, you want to look for a greedy or DP, and the DP would be like keep or don't keep, right? Classic DP problem. Like for every single state, you would just say like, do I keep it? Do I delete it? And then what's like my best result after I do that? But it's kind of tricky with the states here, and I don't know if there's a greedy solution. I wasn't able to find it. Like at first I thought, okay, maybe I want to get rid of some characters that are like by themselves because that would give me something. Because for example, if I have like a 8 and I delete an H, it doesn't give me anything. So the only time you get things from deleting characters is like if you have one character and you get rid of it, or if you have 2 characters and you get rid of one of them, right? Like if you have like B2 and you can convert this to B, you'll get something. Also, if you have something like B10 and you convert this to B9, like you'll get something there. But it's kind of tricky to code that up. So I don't know if anyone was able to do that. I was looking through the solutions and I didn't see that. So I would decide to go with a DP. And for DP, this is also very tricky because you need to know like the states. They are kind of generous with the constraints. So this is where you need to be good at figuring out like what are the states I need and is this going to pass, right? So ideally, we want to have a situation where we traverse letters and do a keep or don't keep kind of thing, right? Because that would make our DP not have like an nested for loop in there. And so if we can like get enough states to have this possible, then this is what we want to do. So let's just think of like the states we want to have, right? For like keep or don't keep. So obvious state right away is obviously the index, right? Like you have to traverse it. But then what else do you need to know? So another sort of obvious one is kind of like how many deletions did I do or how many do I have left or some kind of like things, right? Now the next ones are kind of tricky. And basically the thing that you want to think about is like when we get to a letter, what do we need to know? Like let's say we get to this A, like we have a string, right, of like, let's actually draw this out. Yeah, so let's just make like an array of some characters. And let's just say we have like A, B, A, B, C, A, B, or something. So let's say we're on this character and we want to know, like, if we want to keep it, if we want to delete it, or what, right? So essentially, the problem is we kind of have to know the state of the previous stuff, I believe, because if we have a bunch of A's beforehand, we need to know like how much this A adds to our length of the string. And there's no way around it because like if the previous character is a C and we want to keep the A, let's say, then then this A is going to cost us something. But if the previous character is an A and it had some count, that's the other thing, right? If the previous character was an A and now we have an A, there's different things that can happen, right? So if the previous character was an A, but we had, like, say 9 of them, and we added another A, now this is 10. So this does actually cost us like another space. But if we only had like 2 A's and we have an A, now this doesn't cost us anything. So this is kind of what we need to have. So we need to have, at least as far as I thought of, maybe you can make it a little bit less, is you need to have a previous character, right? To know like, what is this a different character? What do we have to do? Because we do have to know if it's a different character, because that's going to determine, like, do we want to keep it? Do we want to delete? And also, what's the total length of our array, right? We have to know that. And we also have to know previous character count. You could combine this into, I guess, like one thing. Like, you could combine it into a string if you wanted to, which would be like A23 or something, right? Like, that would be fine. Or like some kind of thing like that. And you do need that because, like I said, like if you had 2 A's and you add an A, well, this doesn't add anything to our length, right? But if we had 9 A's and we add an A, then this does add to our length. And there's kind of no way around that, I think, anyway. So these are the things we need to know. We need to know the index we're at. We need to know how many deletions we have left, or whatever way you're doing it. You can either start at K, go down to 0, or start at 0, go down to K. I think I started at K, go down to 0. Then we need to know the previous character we were at and the previous character count. And this will allow us to just pick a delete or don't delete for our character. And like I said, you want to be able to good at figuring out constraints. So let's think of the constraints here. So the index is like 100 characters. Deletions, I think K is 100 characters. Previous character is 26 characters. And previous character count is going to be like 100 characters again. This is roughly like 10 to the 7th or so, which will pass, right? Roughly. So I think anything under like 10 to the 8th, I think, passes. So this like barely passes. And when I coded it, I actually got a pretty bad runtime. So I think you can probably do some optimization. It did pass, but it's kind of barely. And most of the solutions I got weren't much better. Like when I coded this, it was like 5,000 ms or something, which is like pretty bad. But most of the solutions I looked at were like 3,000 or something like that. So now that we know that these are the states, right? Essentially, how is this problem going to look? Like what is our actual other stuff? What's our like base cases and so on? So our base case, you can do this a few ways. I personally, in my code, made sure that if I can't make a deletion, then I don't try to delete. But you can have in your code just try to always delete, and then if your k is negative, then you deleted too much and this is invalid. So what I did in my solution was I have a base case of just index out of bounds, right, as always. So index out of bounds. Now we want to think like, what do we want to return if the index is out of bounds? So the way I handled my code personally is, and I'll kind of show you, like we'll do a little dry run, is anytime we get a new letter, right? Like let's say we had some letter with a count, like let's say we had A with a count of 4, and now we're on letter B. Well, now if I choose to keep B, I'm just going to say the number, like the result of my array is whatever the previous thing was. So this will be A with a count of 4 will be 2 letters, so it'll be 2 plus keeping this B. Right? And if I want to delete this B, then we'll go over that as well. But essentially, I always updated the length of my array right when I got to a new letter or the end of the array. So essentially, when you get to the end of the array, what I did was I just said, let's take, let's move this over here. Okay, so index out of bounds. So let's take last letter and count and figure out length there, right? So if the last character was like an A with a count of 2, I'd say that count was 2. So I would just return 2 plus, or I would just return 2, for example, right? And that kind of makes sense. And I'll walk through how this works. Now, the other thing I did was if our index is out of bounds, like let's say we go through our whole thing, if we have deletions left, then this can't be the best, right? So for example, let's say we have a string of, this is like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 characters. We get to the end over here and we still have like k equals 2. Well, this can never be the best because we could have just deleted something else, right? So this can never be good. So basically what I did in this case, I just returned infinity. Now you could just return something else, but I think this makes sense because yeah, I think this makes sense to do it. Because essentially you're saying, this there's no way this could be good, right? Because like if I had some deletions, because k is never k is a length of the string or less. So let's say I deleted some numbers. Well, I could have just deleted more, and it would have, and deleting more is always going to be either better or the same. So I don't want the solution of where I delete everything. So that's going to be the base case, right? So if we do have deletions, then this can't be the best. Now the recursive cases. So remember, our goal was just to delete or don't delete, right? And so what do we do if we want to delete? Like, it's kind of hard to do a dry run just because this gets so big. But let's say we're on some letter and then we have something. So let's say we're on this B, right? And we didn't delete anything up until this B. So what's going to happen here? So this index will have some index, right? This will be index 0, 1, 2, 3, 4. And essentially what we're going to have is, or actually, let's say we didn't delete. Let's say we didn't delete. We're on this B first, right? So we're on this B, and we our previous thing is like an A with a count of 1, right? Like, what do we do here? Well, if we want to keep the B, that means we're writing whatever we had into our array, right? We're writing this in. So if we don't delete, there's two situations here. So same characters and different characters, right? So if it's a different character and we don't delete, like we say we want to keep this B, that means we have to write in this A. We can't like delete it, right? Because we chose to keep it in our previous DP. So when we pass this in over here, essentially if we have a different character, we are going to calculate length of string with previous character and count, right? So for example, if we had an A with a count of 1, remember you can just write that in as A. So this will just be 1. So you take that and then you add plus dp of index plus 1. And then because you chose to keep the B, now you're going to have the character that you are currently on. So current character with a count of 1. And because we chose to keep, not delete, then we're going to have our old k value. So it's going to be something like that. Now, if it's the same character and you want to keep, that one is pretty straightforward. So essentially, if you were on like an A, right, and you let's actually do that one. So let's say we are on, let's say we choose to we choose to keep everything. So we choose to keep this letter, and then we get to this letter, and now our previous count is A with 1, right? Or actually, let's even say we chose to keep this A, delete this B, keep this A, and now we're here. So our previous count is going to be A with 2. And so the same character is pretty straightforward. We just update our count, right? So we will just call dp. We're not writing this in yet. We're just going to update. So basically this A2 needs to just get changed to A3, and then we're going to pass that into the next state, right? So our count will just be dp of same thing, index plus 1, and then it's going to be the old character, so that same last character, and then that's just going to be count plus 1 and k, right? So that's going to be the things for, let's move this over here. That's going to be the things for don't delete. Now delete is going to be pretty easy. So delete, like let's do a delete example. Let's say we are here. Let's say we are on this character, and now we decide to delete this A. So if we delete this A, then our previous character will be the same, right? Because essentially we decided to, in this current iteration, we decided to delete this B, keep these two A's. So if we delete this A, then our previous part is the same because we're essentially skipping. It's like the balloons thing where the DP, if you're skipping it, then your previous is going to be the same. So all you really need to do is just add a deletion and pass your previous forward. So this part is just going to be dp of index plus 1 again. And then the last character is going to be the same, and the count is going to be the same, and now you have one less deletion left, right? Because we chose to delete. And that's pretty much all the things you're going to have, right? So if you delete, and like I said, in my code personally, only if we can, right? So if k is greater than 0. So if we don't have any deletions left, in my code, I just said we can't delete, and we can always choose to keep, right? We can always choose to keep and then figure out at the end, like, what's the best. And like I said, in the base case, we're just going to have this, like, we go through this whole array, and if we didn't use up all of our deletions, this can't be the best. And I think that's most of it. So, yeah. And, oh yeah, like I said, at the very end, let's kind of walk through what would happen here. So let's say we get to this point with, like, let's say we just chose to keep these 3 A's, and let's say we, like, deleted all of this. You know, our K was something, we chose to keep these 3 A's, and we get here. So we get here with a with a count of 3, and now we're just basically going to say, okay, let's say our deletions is 0, like our deletions left is 0, so k is 0, so we're good there. Now basically what we would say is like, what's the length of this thing? It's 2, so then we will just return 2, right? Because like I said, I'm only writing my numbers into the array when I either get to the end or I'm on a new number. So anytime I get to a new number, I'm writing it in, or I get to the end. And until then, I'm just storing it in, storing it in, storing it in, because I only want to write it in once I know my final count, because the final count is going to determine how long it is. Yeah, and I think that's most of it. So let's actually take a look at the code for this one. Scroll up. And yeah, so I made a little function, a helper function that just returns the length of, like when you pass in a letter and a count, right? So if I pass in like a with a count of 2 or something, how long that should be. So if something has count 0, I'm just going to return 0. And by the way, I didn't mention this, so I'm going to initialize this dp function because I'm going to start, this is kind of the same trick I used before, I'm going to start at a letter that can never have a count of the same letter, right? So I'm just going to pass in like a dot with a count of 0 in the beginning. Because this is only lowercase English character, so I'll just pass in a dot with a count of 0. That way, whenever I'm writing in my letter, it'll always have a count of 0. So if the count of 0, this takes 0. If the count is 1, return 1, right? Because if we have like 1a, this can be represented as a. Otherwise, let's just take 1 for the character. Let's take our number, right? Whatever our number is, let's say it's 10. Get a string and just get the length, right? So if it's 10, 10 will be 2 characters. If it's 9, it'll be 1 character, and so on. So this little helper function should be O of 1. Now I did see some stuff in solutions where people actually updated their count in real time, and I guess that makes sense too. So they would just say like, okay, when it goes from 0 to 1, that gets updated. Then when it goes from like 1 to 2, I think that gets updated. Then when it goes to like 10, that gets updated, and then 100, it gets updated or something. But this is fine as well. So this is basically an O of 1 function. When we're writing in our string, how long is it? Then this is our cache, and kind of weird, but yeah, in Python you can use just a tuple of all these things, and it'll be fine. In other languages, you probably have to deal with some kind of like string or something. And here's our out of bounds check. Like I said, if we haven't used all of our deletions, this can't be this might actually be the best, but we can always try using all our deletions, right? Like if we have some deletions, this might be the same as something with all our deletions. Because for example, let's say we have something like this, and we have like 2 deletions. So technically here, if we use all of our deletions, we will have A6. And if we don't use any deletions, we'll have A8. So they are the same, but using all our deletions can never be worse. So we're just going to say, even though this might be the best, we're just going to always pick one with 0 deletions, because that's going to guaranteed either be the best or tied for the best. Then we just cache the result and return it. And I wanted to cache it because normally I just return it away, but because here I actually have some checks, I decided I think caching is going to be a little bit better. If you just have like a super fast operation that you don't have to do anything, you can probably just return straight away. Okay. And so you initialize your result to infinity, and now you basically just look like what things you can do, right? So if our deletions isn't 0, if we have deletions left, then remember when we delete the letter, it's pretty straightforward. You just keep the same letter as before with the same count as before, and you just decrement your deletions by 1. And if you want to keep the same letter, there are 2 things, like I said. If the letters are the same, then you just increment the count by 1. And if the letters are different, that's when we're going to be writing in our count, right? So we call counts on whatever we have. So let's say we had like A5 and we're on a B. Now we have to put in 2 letters. So we're going to pass in 5 up here. We're going to pass in 5 into this counts function. This will return to us 2, and then we will add 2 to the new letter. Yeah. And so these are the things this is the 2 things you can have, right? The old result and the new letter. Then you just cache and return. And like I said, initially I pass an index 0. The last letter is a dot because I want to make sure it's different from the first letter. Not even the first letter. I want to make sure that it doesn't exist in our array, because let's say we do delete like 10 letters. I want to make sure that this will always have a count of 0. So I just pass in a dot, and then I pass in k, because that's the number of operations you have. So like I said, when I actually ran this, let's reload the page. Might be down. Okay. So yeah, when I ran this, I actually got like a very poor runtime. It passed, but barely. Okay, apparently now it's twice as fast as it was, which is super weird. But when I looked at other people's solutions, so like, yeah, so no matter what solutions I had, it was like this. But even if I look at solutions that were really fast, like let's say I'm curious, let's see if it's faster now. Because when I copied solutions that were really fast, mine was still really slow. Okay, this is faster now. So I guess this is let's take a look at this one really quick. Okay, so this is using DP. Yeah, okay, well, definitely not doing this kind of thing. It seems crazy. Let's look at another one. Okay, this looks kind of similar to the other one. Okay, so you can space optimize it. So maybe if you space optimize it, it is actually significant. Like, I know you can space optimize it a lot, so I guess we could talk about that. So let's actually go back to our old code. So what we can do here is, now you can't, I mean, it's only going to get rid of one dimension, but it will make it a decent amount faster, right? So every time you recurse to index plus one. So you could get rid of one of these dimensions. So you could get rid of either the index dimension or the count dimension. The index dimension is going to be better, obviously, because it can get bigger. So then it would be space is going to be like this, which will be like, instead of 10 to the 7th, it'll be like 10 to the 5th, which will be like a decent amount faster. But I don't really want to space optimize a 4D dynamic programming problem. So if you want to do that, that's what you would do. You can space optimize for getting rid of this dimension. So yeah, let's talk about the time and space. So essentially, like I said, in our goal in our DP was just have a keep or don't keep. So that part is O of 1. But our dimensions are index, which is O of n, k, which is O of n, last character, which is O of 26, and, well, I guess 27 with the dot, but the dot only appears in one spot, and the count of the previous character, which can be O of n as well. So it's like n cubed times 26, which is like I said, roughly 10 to the 7th. And space is going to be the same. So n cubed 26. So I definitely think the hardest part about this problem is figuring out these states. And also, it's not super clear. Like, for a lot of these problems, they give you these constraints. Like, they'll say S length is 100, but in reality, you can do this in, like, 2 states. So it is kind of hard to figure out, like, is this actually the optimal thing? And like I said, you can technically get rid of one. The runtime, though, would still be n cubed, but I think because you don't use a cache, like, I think making all of these tuples is actually kind of like slower than having like an array for all these things. So yeah, having an array of all these things, but like I said, you'd have to have like a 3D array. Gonna be a pain. You could do it. Definitely a good lesson on space optimization. So if you do want to do that, definitely you could do that. Get rid of this dimension. But yeah, it's gonna be all for this one. Hopefully you liked it, and if you did, please like the video and subscribe to the channel.